this pressure, under this weight, we are diamonds. And I feel my heart beating. I feel my heart underneath my skin. I feel my heart beating. You make me feel like I'm alive again. Alive again. Oh, you make me feel like I'm alive again. Said I can't go on, not in this way. I'm a dreamer, die by light of day. Gonna hold up half the sky and say, only I own me. And I feel my heart beating. I feel my heart underneath my skin. Oh, I can feel my heart beating. 'Cause you make me feel like I'm alive again. Alive again. Oh, you make me feel like I'm alive again. Turn your magic on, and you she'd say everything you want's a dream away. Under this pressure, under this weight, we are diamonds taking shape. We are diamonds taking shape. We've only got this life, this adventure, oh, that and if we've only got this life, you get me through. And if we've only got this life and this adventure, oh, that I wanna share it with you, with you, with you. See you, see you.
Nosy, I don't think the webinar has has the webinar started? Okay, great. Wow. Welcome back, everyone. We're almost at the end, and I hope you guys are going to be feeling alive again because you were doing hard things. So in this week, we are going to be, or in this session, we're going to be discussing your Gaussian occasion, or however you guys pronounce it. There's no master of pronunciation, mixture model. So it is still a clustering algorithm, but now it's not necessarily, remember last week, again, we'll do a revision on how I spoke on hard clustering and soft or fuzzy clustering, as well as hierarchical clustering. But now maybe if soft and fuzzy didn't make sense, it would be a whole lot clearer in this session. Right. So I'll be a host again, me, as always. We're going to come to an end, and I won't be able to see you guys. I have sessions with you where we get to discuss and comment on how the program is going, but it's definitely been an honor to have been part of the journey. So, rules of engagement. If you got any questions, post them on the Q&A section. Feel free to use the chat liberally, respectfully, and it will be open ad hoc throughout the session. As you know, I like engaging, I like asking questions, and you might as well start putting those ratings that I usually ask because that question is definitely coming up. And lastly, make sure you listen, learn, and engage. So in this session, it's basically understanding and applying GMM or Gaussian mixture models, right? We're gonna hop onto a quick demo, but before we do that, in the chats, how are you feeling now, especially now that we're coming to the end, about the machine learning track on a scale of 1 to 10? What mood? How are you feeling? How's the excitement of finally reaching the end? Where do you stand? Yes, no, no, yes. Are you guys there in the chats? I'm sure it's not, doesn't take that long to put in a number. 10 out of 10. Oh my word, Winfred Piri. That just made my afternoon. Absolutely love it. I always usually get 9.999. I'm sure it's gonna show up now. But oh, brings me so much happiness to know that someone is feeling 10 out of 10, feeling awesome. I'm sure you're happy that you're finally coming to it the end. It's been a long, 12 months maybe, throughout all the tracks, not just ML. I mean, like you went through data analytics, you went through Python, and then you're now here at ML and you're at the end. Is there no one else who has a specific mood? Is it just Winfred? Or you just over this now at this point? Happy 10, that is ending, but 5 understanding. And that is okay. I'm glad the experience was a 10. That is not necessarily experience. I'm not sure if that's part of the experience. But at least we got a 10 out of you. But 5 in understanding. Juliet, I remember we have been having this conversation, and I'd hope maybe we would have gotten to a 9 at this point. But you know what? You maybe you might not get your full 10 from us, but I'm glad we could have given you 5. And as the journey continues and as you enhance your skills and your understanding in machine learning engineering, you'll reach a 10. But I'm glad we were able to give you that 5. Right, let's hop on to our demo. Right, I'm going to share that. Is it this one? No, it's not this one. This is the incorrect link. Let me quickly just stop share, and because I know you guys are going to have me for not sharing in the chat. As stated, I have learned from my mistakes, and I'm here to do better to make sure that we can be coding alongside each other, or you guys can go through it as we move along. Just want to make sure I gave access, share. right? Where are we? We're here. Right, that is the link. Let me get back to sharing my slides. Oops. Okay, so now I'm sharing that. We are here. Right, quick introduction. So as I stated, GMM is also a clustering algorithm. It just works differently. It applies soft clustering rather than k-means, which is hard clustering. Now, who can remember what's the difference between soft and hard clustering in the chat? Who can remember the difference between soft and hard clustering? If k-means clustering is hard clustering, what can you derive from that? Like, okay, k-means clustering is hard clustering. What does that mean? What does that mean? Hard, the data point either in one or out a cluster. Exactly. You cannot belong or be like, oh no, I'm in cluster one, or I'm in cluster two, or I'm in cluster three. You cannot, let's say, be let's say you're working and maybe cluster of, okay, I'm not sure which one to give for this one. Let's say areas. You cannot be in multiple places at once. So the chances that you will end up in South Africa or Nigeria or Kenya, if those are the three clusters, then you cannot be in one of the clusters or be in this cluster and another cluster, right? Hard clustering is distinct. We specifically state that this point belongs to this cluster. And some of the matrix that we worked with was your within cluster similarity and between cluster similarity. We wanted to make sure that the points in our clusters are tightly closed or tightly placed in this cluster or are centralized around their centroid, right? And that basically helped us define that this point is in this cluster and how well our clusters have been distributed. A reminder is that it is called unsupervised learning because the algorithm does not require labeled data. We give it data and it understands the pattern with the different features. Okay, so when we were working or when we were plotting, and let's say we use the first principal component and the second principal component, you saw that the centroid would be indicated with 2 points, sort of like coordinates, like the x coordinate and the y coordinate. But in that case, it shows the coordinate in principal component 1 versus principal component 2. That is where my centroid is. So this is again an example of how k-means clustering works. Remember, it just randomly places centroids and then start drawing data points towards those centroid that are similar, right? And of which then starts generating an average. And these points come closer until there is convergence, right? So we've reached the point where there's not much changing as we keep calculating the average within the clusters, right? And that's what helped us understand the Albo method, or that's where the Albo method came in. It told us when should we stop? How many clusters should we stop at as well? So k-means clustering is one of the most widely used unsupervised machine learning algorithm for grouping data in clusters based on similarities. You can read through the detailed background of this, where you have partitions and Ks or clusters, right? So we had the different partitions, each in the cluster. We had your within cluster sum of squares, which is basically the variation as well within these clusters. We wanted it to be as low as possible. Please note, this is within cluster sum of squares. What is defined here is within cluster similarity. So we want within cluster similarity to be high, but we want the within cluster sum of squares to be low, right? When this is low, this means that my data points are not too different within the clusters, right? One data point or the next to the centroid on your right versus next to the centroid on your left are not that different, or the difference is not that different, it's not that high. Some applications of k-means clustering included customer segmentation, image compression, and so forth. Again, we mentioned the ALBO method and how it gave us or helped us identify the optimal number of clusters. So these, remember, with the ALBO method, we also use WCSS and which was BCSS, right? And we had a curve that was decreasing and a curve that was increasing. And then we created one matrix that then helped us by the peak show the number of clusters that were at optimal. Even though with the ALBO method, we would see that, no, man, we need six clusters using WCSS, or we need 6 clusters using BCSS. Right. So that's just a revision. So you can see the difference between k-means clustering and once we use our Gaussian mixture models. So as I showed in the example here, or in the image here, we have hard clustering where you either belong to one cluster, right? That's why you have clear separations, right? You have hierarchical clustering. I hope you guys went and watched that video. I know last week my sound wasn't working so great, but I had shared the link to the video and I hope you went through it and saw how hierarchical clustering works. Then today is where we're going to introduce soft and fuzzy clustering. And this is where we are going to be applying our Gaussian mixture model. So in this case, this doesn't just take points and centroids and say, okay, no, this distance from this point, the distance between this point and this centroid is somewhat okay. Basically using nearest neighbor distance, right? We're not going to use that. With GMM, I don't want to say the whole term now, like it's a tongue twister. It is a probabilistic clustering algorithm where the machine learning model basically groups data points into clusters based on probability. Like, what is the probability that this point would be in this cluster? So that's why then it doesn't use hard clustering, or we cannot distinctly say we can't, or with probability especially, we can have a high probability, if in statistics, but you never say that it is definitely this that is happening. No, you use terms such as the probability of this point being in cluster 1 is quite higher than all other clusters, or this point is most likely to be in cluster 1. Probability we never have certainty unless we have 100%, which that has a low probability of getting any 100% point in anything that you do. When I was doing statistics, it was stated 100% probability, you need to check your calculations, right? So intuition is that, imagine you have a customer data containing age and annual income. Instead of drawing hard boundaries between customer groups, GMM asks, what is the probability that this customer belongs to each cluster. So as you can see, we're not just limiting you to one cluster. Now GMM is like, okay, I'm going to give you an option. I'm going to give you options. And we're going to see how each of these points work in either of these clusters. And that's when we introduce the probability. In this case, you can have 90% probability of belonging to cluster A, or 90% or 10% probability of belonging to cluster B. This is then what we call soft clustering, whereas K-means is hard clustering. Each point is in exactly one cluster. We cannot say, oh, it's in one cluster, but it could be in the other cluster. No, that's not how K-means work. K-means get straight to the point, and that could be some of the limitations. Right. So once it starts predicting, remember with K-means we draw up the number of clusters, we fit the model, we scale out data, we call the model and fit the scaled data, and then we run predictions. What is it predicting? The cluster in which it belongs to. So in this case, GMM also does the same, but it will assign a cluster based on the highest probability that the specific observation has. So for example, customer 1 will be assigned cluster 1. This is when cluster 1 has the highest probability for the customer. So what is basically happening here is that we have created 3 clusters, or we have given the model and stated create 3 clusters. And once it is creating these 3 clusters, for each observation, or let's say for each customer, it gives a probability on how much or how well it would be in each cluster. So this is cluster 1, cluster 2, cluster 3, and that probability is just for one customer. And then GMM decides that, okay, as you can see the description, this tells us the customer mostly belongs to cluster 1, but shares characteristics with cluster 2, right? Does it make sense? Hopefully, are we on the same page? So there is a video that's going to show, I want to show more visuals on the Gaussian mixture models. So remember, Gaussian is basically a bell-shaped normal distribution. You can, I think in some of your probability tables where you have your z-scored, they could either write it as your Gaussian or z-score or normally distributed or bell-shaped. So let's look at some visuals on how Gaussian mixture models work. Okay, hopefully my sound does not fail me this time.
Hello and welcome. In this video, we're going to talk about the Gaussian mixture models. Why do we need them? Journey we've had so far was something like this. We've seen clusters which are nicely separated, and every single point is assigned. Hello and welcome. In this video, we're going to talk about the Gaussian mixture models. Why do we need them? Journey we've had so far was something like this. We've seen clusters which are nicely separated, and every single point is assigned one unique cluster label, which is known as the hard clustering, which means every single point is so nicely separated from the other points that it can be only given one membership. And it is actually doable for this kind of data that you see on the screen. But what if our data was something like this? It's all mixed up. So if you look at it carefully, there is a potential of looking at a cluster like this, which is more of a cluster for these orange points, and another cluster like this, which is more of a cluster for these blue points. But why a conventional technique like K-means would not work here is because the center of these two clusters is overlapping. And we know that K-means is a centroid-based technique. So it decides the cluster membership based on the proximity to the centers. What if the centers are overlapping like these? In such cases, the Gaussian mixture models come to our rescue. Let's say we have some data points in a one-dimensional space. So these are different data points that we have, and these are all real numbers, which means they are numerical values. These are not classes like 0 and 1. These are all real numbers. So whenever some real numbers appear before us, The first thing that comes to mind is a normal distribution or a Gaussian distribution. So the Gaussian mixture model assumes that these data points have been generated using some kind of Gaussian distribution. And to begin with, we also need to decide how many Gaussian distributions we are talking about. So in a way, this is similar to deciding the number of K clusters in case of K-means. Here, we're deciding the number of Gaussian distributions. Let's say we start by assuming that there are 2 Gaussian distributions. So as a part of step 1, we randomly initialize the Gaussians. Note that 2 is just a number that we chose in this example. It is not mandatory that we'll always have just 2 Gaussians. We could have more as well. And we are working on a particularly simple example, which is only one-dimensional data, whereas our data could be multi-dimensional. Once we have randomly initialized these 2 Gaussian distributions, in the next step, we have to calculate something that's known as the responsibility. In very simple terms, I can say it's the probability of belongingness for each point. So for each data point, we need to assign to what extent does it look like a point belonging to this blue distribution or this orange distribution. So for example, a data point here, while it is in a less dense blue region, it still is away from the orange distribution. So it is more likely to be blue compared to orange. This is just an appearance. It will always have a small share of orange, which is not even visible here. Similarly, a data point here, which is in a relatively less dense orange region, is even farther from the blue distribution. So it's more likely to be orange. And what about the data points in between? They're more likely to be a mix because in this region, there is a little bit of uncertainty. Same would be the case with these points. So all these points in the middle would be claimed by both the distributions. The proportions might vary. For example, here, it may be an equal claim from both the distributions. Whereas the points which are very close to the center, which is the high density region for any distribution, might be more prone to get that color. This color coding is something that you can call as a responsibility. So we are saying that this point is more likely to be a point belonging to the blue distribution. So the probability of this point being a point from the blue distribution is higher compared to the probability that this point belongs to the orange distribution. Notice that the responsibility, or just another name for probability as we are calling it, would always add up to 1. So if you have 3 Gaussians, maybe all 3 would claim for each point, but all the probabilities of belonging to these distributions will always add up to 1 because there are only 3 possibilities. In our case, we are looking at only 2 possibilities, and that's why we are saying these will add up to 1. Once we are done with assigning the responsibility to each data point, the next step is to only focus on specific points for particular Gaussians, which means right now we are only going to consider the Now, as per the presence of these blue points, we are going to reconsider distribution assignment, which means we are going to once again compute the normal distribution. A normal distribution, as you know, is characterized by its mean and standard deviation. Mean is where the center lies, and standard deviation determines the shape of the normal distribution. So let's say we come up with this Gaussian as a revised distribution. And similarly, for the orange data points, we once again calculate the normal distribution. Remember, originally we just did a random initialization of these Gaussians. Now we are calculating based on the responsibility. So let's say we find this Gaussian distribution now. So we have these as our distributions till now. Now we are supposed to repeat certain steps. So with respect to these distributions, now let's look at the data points all over again. And once again, we need to determine the responsibility. Notice that responsibility is influenced by the Gaussians, and Gaussian parameters are determined by the responsibilities. So it's kind of a cyclic process. We started with the random Gaussian distributions, computed the responsibilities. Then based on those responsibilities, we revisited the normal distribution parameters like mean and variance. And we are saying we'll once again compute the responsibility. So as per this blue Gaussian distribution, maybe a lot of these points are not closer to the center. So we will say that these points will mostly be blue. When you see this as entirely blue, please note that normal distribution is asymptotic, which means this distribution is not limited till this point, or this blue distribution is not just limited till this point. They extend till infinity. So this would always have some influence of the orange distribution here as well, but that maybe is minuscule. Similarly, these points here, while they're closer to the high density region of a normal distribution, which is orange, they will also have some influence of the blue distribution, but maybe that's minuscule right now. Whereas the points in between would always tend to have more of a mix. So the first difference here compared to the classic clustering algorithms is that these points are soft clustered. We are not saying that these have to strictly belong to one cluster or the other. We are accepting that there may be a mix, but there may be a majority influence of one particular distribution, and we will go by that. And these steps of calculating the responsibility and revisiting the model parameters will be repeated. For example, you may end up getting this as the final output. At what stage do we stop? When do we say that we have converged or we have reached the end conclusion? When we do not see much change in the parameters for these Gaussian distributions. When we continue to repeat these steps, but beyond a point, the distributions don't really change significantly. We say that we have converged, and that's how we will determine the clusters. So once again, to summarize, what is the similarity between Gaussian mixture models and k-means clustering? Just like k-means clustering, this is also an iterative approach. In k-means, we used to iteratively determine the centroids till we finally converged. Here, we iteratively determine the mean and the variance. And this is applicable only when we are dealing with one-dimensional data. The moment we go to multi-dimensional space, we will no longer have just one mean value. We'll have a mean vector. Likewise, we'll not just have one variance. We will have a variance-covariance matrix, which means there will be much more complicated calculations there. But the basic idea stays the same. That's why we try to understand it with the help of one-dimensional example. Now, what is it that's different in case of Gaussian mixture models? Unlike k-means, Gaussian mixture models follow soft clustering technique, which means we do not assume a point's strict membership to a cluster. We say that there is a possibility that a given point could belong to multiple clusters, and we may look at the proportion. While we didn't go too deep into the technicality, these steps that we have followed here confirm that this is a probabilistic model. Why? Because we are assuming that there is a distribution. Whereas in case of k-means, we never assume that the data follows a specific distribution. And the steps 2 and 3 that you've seen here, where we first calculate the responsibility based on the random initialization, and then in the next step, we calculate the distribution parameters based on the responsibility, and alternatively continue to repeat these steps. This is a part of expectation maximization algorithm. Step 2 is known as the E step or the expectation step. Step 3 is known as the maximization step. Please note, the equations related to Gaussian mixture models could be quite daunting because these involve heavy formulae. But for our purpose, we've tried to explain this in the simplest possible way without using too many jargons. So I hope you get clarity on how Gaussian mixture models are useful, in what cases they are more meaningful compared to the k-means. Thank you.
Right. I hope that was helpful. So, who can tell me what form of clustering is the Gaussian mixture model? I think we've said it multiple times at this point. Soft, exactly. So it is soft clustering. And as you saw, it is because points can belong to either cluster or, in this case, normal distribution or Gaussian mixture, right? And as we went through, you kind of saw that the process is almost the same as k-means clustering. Remember, in k-means, we randomly start with centroids, but with Gaussian, we randomly start with Gaussian distributions, whether you want 2 components, or in this case, the components are those bell-shaped graphs, right? You start randomly, and then you start moving along with the responsibility, or in this case, the probability of each point, so that we can align with some of the points that we have. So I've given you a table on the examples, right? Where on the different clustering methods, so your k-means and your GMM, as of hard, soft cluster shape is spherical, meaning like a circle, whereas GMM is any Gaussian shape. Output of k-means is not probability, but for GMM it is. Covariance is not used with k-means, but used with GMM. Algorithm is distance minimization. Remember, that's when we had the within cluster variation, or within cluster sum of squares. There are multiple ways to say it, or within cluster similarity. That's what we were looking at, distance. In this case, we're working with probability maximization, right? So we want to get as clear or optimal. Everything we always do in machine learning is always about optimization. So in this case, we want to optimize the probability that is assigned for each cluster for each of our observations. So you've seen sort of the visual and the theoretical part. So now let's hop on to the practical. We're going to create a synthetic data set, right? Just as we did with k-means, so we know what we're working with here. We're going to have 4 centers, or data that is centered will be 4 centers. I guess you can have 4 means or 4 components. If we're doing k-means clustering, we'd then say 4 clusters. In this case, we're working with GMM, so we're going to say 4 components. But again, when we go through, we're going to act like we know nothing. All right. Then a new one is cluster standard deviation. So in this case, we want the clusters. So each of, you see, these values are somewhat close to each other. The maximum distance is about 0.5, 0.5 for 1, no, 1. So standard deviation of the clusters while we're creating this data is that to allow that overlapping. So it's not easy to create centroids. As you saw in that visual, those centroids, those clusters are going to have overlapping centroids. So in this case, if we have clusters that have similar standard deviation, it's going to be hard to use sort of like a spherical way or spherical method to place our data points. Cool. Then we're going to have a data frame of customers where we have income and spending, and we'll also add age and savings. You can also store it into a CSV, but once you run it, this is what we will have. Hopefully did I run any libraries? Okay. Okay, those libraries are there at the beginning. Right. So as stated, let's pretend there are 4 hidden customer groups, right? We have students, families, professionals, and retirees. Or you could have, like the last time, lower income, middle income, higher income. It depends on the context of your data, and you can then categorize them into those groups. The algorithm doesn't know about these groups. When we give it this data, right, remember we have no labeling. We don't know what exactly, we don't separate and say, oh no, the input variable, this is the target variable. It's just been given data, and it's like, okay, what am I supposed to do now? Same as k-means clustering, GMM does the same thing. So we are going to have our data, income, as you saw, income, spending, age, savings. As you know, we always standardize so that all our features can be on the same scale, so that none or neither of these features take preference over the other just because they're on a different scale, therefore having higher values. So we scale our data and we transform all, basically those features, each of them are then scaled. So the story is that now we're hiring a detective. The detective job is to find the hidden customer groups. Same way as k-means clustering. The only difference is basically the method, right? It's not hard clustering, it's soft clustering. We're not going through centroids in a spherical method, but we're going for means and standard deviation or variance or covariance if we have multiple features. In this case, we do. We're going for a Gaussian mixture approach, right? So you're bell-shaped, not just circles this time. Circles are limiting because most of the time the data doesn't necessarily look like that. A lot of people when I was having conversation with some of my friends, they're stating that K-means clustering is the new random forest. So then, back then, random forest was sort of the hardest model to understand and work with, but now it's okay, you know, it's not that bad. But K-means clustering and Gaussian mixture models are now ruling the brains into how exactly am I going to tackle some of the issues or problems or projects that I'm working with. So remember we had 4 blobs. We had created 4 blobs. So we're going to give it n components, which is equal to 4. Once we call the model, which is here, right? We're going to give it 4 n components. Those n components are those bell-shaped, right? Those bell-shaped, randomly assigning the Gaussian models or the normal distribution graphs across all features, all right? So we believe there are 4 customer groups. The model will try to discover the 4 Gaussian distribution, okay? Covariance types equal full. So this is extremely important because imagine drawing circles around each customer group. We have multiple features, right? Remember, if you remember in the video, we were given a one-dimensional data set. In this case, we have what? A we're working on 4D, right? We have 4 features. So we're not going to be working with just variance. We're not going to see how the points move alongside each other and just look at the standard deviation. We're going to look at covariance. How is the one point amongst the other features moving the other points amongst the other features? As these features move, how does one feature affect sort of the movement of one feature from the other? Hope that makes sense. Okay, so GMM works with circles, ovals, and tilted ellipses. So this one is the one that we're probably going to be working with. Hopefully, I wish I had a visual of this, because we're working on a multi-dimensional or multiple features. We won't be easy to have it even drawn because we're working with a tilted ellipsis plane, or what did we have the last time when we were working with dimension? Hyperplane, right? So real customer behavior is really a perfect circular, or you don't just draw the data. Even if you create your principal components, real customer data rarely becomes a perfect circle. And that's why GMM is more flexible. It doesn't just create circles like your K-means clustering. It creates all 3 of those that were just mentioned. So this answers one of your questions. GMM works well for non-spherical clusters because of the full covariance matrix. And when talking about clustering, especially Gaussian mixture models, covariance has a slightly different meaning. It doesn't mean, well, in this case, instead of measuring the relationship between 2 variables in the whole data set, covariance describes the shape, size, and orientation of each cluster. Right. Hope we're still on the same page. Should probably put that in bold for you. So now we call the model, and how we call the model is that we import our Gaussian mixture from the sklearn mixture. We call the n components, which is 4. We have covariance full. This allows us to then call either all possible, methods, either circles, oval, or tilted ellipses. So as it's training, it must find that perfect Gaussian shape or Gaussian model and iterate through it until it finds the optimal, don't want to say the perfect, but the optimal shape and movement of those bell-shaped curves that were shown you. So when it was explaining in the video, they kept moving. Right? They kept moving and kept moving until it reached its optimal position of those Gaussian bell-shaped graphs. I'm trying to find the perfect term to just help you understand. Right. So we fit this model. Right. So this is when the learning happens. The algorithm repeatedly asks, where do I think each customer belongs? So just like in those points, we have 4 components. It repeatedly changes what? Its mean and covariance, right? Not just variance, we are working with multiple feature. If we're working with one feature, then we could have, or just one dimension, we could have been using, as stated in the video, just mean and standard deviation, or mean and variance. But in this case, we're working with multiple features. Therefore, we are going to be working with mean and covariance. Right, so it keeps changing as it moves. The same way that when we were doing with k-means clustering, the centroids kept moving. We keep moving until we have reached optimum. Okay, so as stated, it repeats until it cannot improve. This process is called expectation maximization, right? So basically, imagine 4 managers trying to recruit customers. Initially, nobody knows who belong where, and the groups are random. So the expectation step, right, to get the maximum expectation, obviously, is the algorithm asks, what is the probability this customer belongs to every cluster, right? So probability of going to cluster 1, cluster 2, cluster 3, cluster 4. We have 4 components. So this is just an example. We have for 1, 65%, for 2, 20%, for 3, 10%, and for 4, 0.5%. So instead of saying that the customer definitely, remember when I said in the beginning, instead of saying that the customer definitely belongs to cluster 1, it says there is a 65% chance that the customer belongs to cluster 1. And this is why then it is called soft clustering. Right. So how do we get there? Remember, we have fitted the model. We fitted the GMM model. We told it in 4 components, covariance, and obviously random state for reproducibility. We then ask it, just like any other, to predict the clusters for each of the customers, each observation. And as you can see, once you run this guy, you'll have cluster 1, customer 1 is in cluster 1, customer 4 is in cluster 2, customer 595 is in cluster 3. Remember, cluster 1 is technically 0, so clustering or numbering in Python starts from 0. Therefore, we have 0, 1, 2, 3, 4, 1, 2, 3, right? Those are the 4 components, or the 4 Gaussian mixture models that we have. Not models, Gaussian models, Gaussian graph, Gaussian distributions, Gaussian components. I don't want to say clusters, but they are clustered. They just have a Gaussian shape rather than a spherical shape. Right, then we calculate the probability. Okay, so I'm just going to use, we had created 600 data points, right? So we're not going to print all of them, but this shows the probability that each observation belongs to each of these 4 components. I'm going to call them components. So in cluster 0, cluster 1, cluster 2, cluster 3, each of these are the probability that it belongs to a specific cluster. So I want to ask this question correctly. For observation 1, which cluster is it likely to belong to if you're looking at the values? So this is observation 1, and the probability of it belonging to a specific cluster, 0, 1, 2, 3. So which cluster is observation 1 most likely to belong to? So in the chats, I think I've shared the link to the notebook here. In the chats, which cluster is observation 1 likely to belong to? Are you guys still here? Two. Adil, when you say two, I'm assuming you're saying 1, 2. Or is it 0, 1, 2? Okay, right. Hopefully you meant 1, 2, which is this guy here, because it has the highest probability. And if you look, we already knew that from there, because that prediction was already given in a table here, right? This is giving us the actual prediction on which cluster it belongs to, whereas GMM predict proba gives us the actual probability in which that it would most likely, or chances of it most likely belonging to that specific cluster. Great. Then what happens when probability is, just want to remove these chats here. What happens when probability is fairly distributed into two clusters? So not necessarily fairly, but somewhat shared into two clusters. So the customer resembles two different customer groups. So instead of forcing them into one group, GMM recognizes uncertainty. So this answers customer belong partially to multiple segments. But obviously, if it wants to predict distinctly or give a hard assignment to an observation, you can use the argmax function so that it can just round off to round off the probability of each cluster, and the one with the highest just belongs there. Okay. Then you get your k-means as well. So k-means then gives us the means for each feature, right? So remember, when we're working with k-means clustering, we had principal component 1 and principal component 2, for example. And when we looked at our centroid gave us, as I stated, coordinates. The value at where it stands on principal component 1 and the value where it stands on principal component 2. Correct? So now, in this case, we are calculating as stated means. So in this case, the means are the means of every feature. We are working as stated on a hyperplane. Very hard to draw this out, but we're working on a hyperplane. Therefore, we have means at four different features. In this case, it would be, if you look at our features, income, spending, age, and savings. So that is the mean for each cluster. So in each of these components, so each of these Gaussian mixture, each of these bell-shaped graphs have a mean of income, 0.09. What else do we have? Spending at 0.944. We have age at 0.093. And we have savings at 0.944. Right. This can be, remember, this is synthetic data. You can put this data and scale it and say, this is in thousands, this is tens, okay, this is in hundreds, maybe that's age, and so forth. Right. Then we have weights. The weights tell us the percentage of data each cluster contains. So all of this, 1, right? So if we were to create a loop right now, say for I in, let's call this array, what are we going to call it? I'm going to call it M, in M, and I'm going to say create a counter. And we're going to say count is plus equal to I. And then we'll return print count. Oh, print count. This should all add up. What did I do? M is not defined. Oh, I didn't run this yet. M return okay, you know what? Let's just print outside the for loop. My bad. Right, as you can see, they all add up to 1. M is equal to the weights, so the percentage of data each cluster contains. So cluster 1, I don't want to say necessarily cluster, but you guys get what I mean, I hope. Component, so component 1, if we run that, let's call M. Component 1, we have 0.27, component 2, or 0.27% of the whole data. And then component 2 is 0.2499. Component 3 is 0.2515. Component 4 is 0.22661. And all those then add up to 100% because then all clusters contain altogether the whole data set. So each of the clusters have been assigned, each of the points have been assigned to a cluster. Great. Now, just like any other model, we have evaluation. Ooh, that word, evaluation matrix. Matrix, right? Right. So what does it measure? So you have your Bayesian information criterion. It basically measures how well the model fits the data and how complex the model is. Now with this guy, you need to be aware because once we run this value here, do you see we have negative 11,264, but that doesn't tell us much when we just have one value. What we want to look at or what we want to test is, what did we call this guy? Let's see what we can do. How well it is performing with different components. All right. So for example, let's say, what did we have? Let's try and have 4i in, how many, let's test in range. Is my range not changing color? Anyway, in range of 1 to say 4. No, we already did 4. Let's say 6 there. Right? And we're going to copy, where's that GM? Where's that GM here? Basically, we're going to copy this guy and we're going to fit our X scaled and see how each one performs with different components. So that's how we basically read the BIC. Make sure this is in my for loop. Okay, GM, are we on the same page? Yes, we are. Let's probably save these. I'm gonna call them big scores. Scores, yeah. So we're gonna store them in empty list. And then every time we calculate a score, we will append that score here. So let me think. I think I'm running out on my for loops. Are we going to have it in or out? Let's have it in. We're going to say big scores dot append. What do we want to append? Just give me a moment. My word. Okay, we want to append the actual, yeah, we want to append the actual big score of the fitted data. Make sense? So we're going to say GM dot the big score of the X scaled. Hopefully I get that right. Man, would it suck if I don't. Right, so this is going to run through. It's going to get the scores for each of 4i. Why did I say 4i? We need to say 4n. Right. I'm so used to having for loops, so I just automatically run to I. Right, now let's probably store this in a data frame. Just want to make sure X scaled is already stored in our data. So do I want to save? Let's save it in the data. What are we going to call it? Results? Results is equal to PD data frame, right? Maybe we'll have a dictionary of the number of components, so of n, and of the BIC scores. Okay, so let's say my word, components. Did I close that? Components. And those components are going to be basically, well, we didn't save, well, might as well have range again of 1 to 6. You can change that range and see which one works for you or which one you would prefer, obviously. You don't have to have 1 to 6. And then we'll have the let's call it BIC. And then we're going to store, let's call big. Okay, so already appended it. So we'll call big scores. Of course. Hopefully this works. If it doesn't, then I don't know, big underscore scores, and then let's see what results look like. If we get an error, it happens. Big scores. What did I do here? What did I do here? Oh, the dictionary. I closed the dictionary. See? Errors happen. You just work your way through. Right. So now we have for each number of component, what is the big score. So then you would look at where you have, I guess, you want to choose the model with the most big score. So you can increase this to, you can increase it to 20. Okay, I'm not going to do 20 at this point. I'm just going to keep it at 6 because it's going to print a whole lot. But you can increase your number of components and see which one works well for you. And then the one that has the lowest big score is the one you want to select. All right. So these are some of the matrix that we have. You also have, I think another one, it's Ike. I'm just trying to remember what the name is. Excuse me. Oh, excuse me. I'll remember it. I will remember it. I haven't worked with Gaussian mixtures in a while. So these are sort of like this is almost the same as your elbow method, right? Your elbow method, we then had to select the number of clusters that we wanted to use or create based on the elbow method. This is the Gaussian mixtures elbow method, right? It helps you balance to see the number of components that you have. Because imagine having multiple components. At this point, each point will have its own Gaussian mixture. You might as well, if you're going to reach up until 1,000 components. So likewise, you want to make sure that you select the optimal number of Gaussian mixture models or components. Right. I think I'm going to close it off here. I have shared, so I haven't shared this part. Hopefully the notebook didn't have this part, so hopefully you can just add it while you're there, or I'll just upload this one again in the slides and you can get the updated version. Are there any questions before we move on? See. Oh, sorry. You know, Adil, I thought I shared the link with you, but I was sharing it to just hosts and panelists. My apologies. Okay, why did that move? My apologies. I thought I had shared with copy link. I already thought I'd shared with you. And I kept pasting, thinking, got the notebook. Right, are there any questions that you guys have before we can? Any questions? Nothing? Yes, no, no, yes. Right, then let's quickly launch that poll. The poll will be launched. Please make sure that you complete the questions in the poll while I head on to next steps and final announcements. So your next assessment is due on the 27th of July, 2026 at 11:59 GMT. This is your Gaussian mixture models and geospatial data. It is an MCQ, so you won't be needing that much coding. The recordings to this session will be shared with you, and you will find them in the ML-04_2026 program hub on eHub. And remember, you're not alone in the community. Engage with your squads, ask for clarity, and post your wins, challenges, and new insights on your squad spaces. Yes, we're almost there. We're almost at the end. Next week, we will be introducing, I think, the Kaggle competition. So based on recommendation system. So make sure you tell your friends and your friends' friends to come so we can discuss on how you can sign up and join the competition as well. Please note that the Kaggle competition does not count for marks on your assessment. So that is just for you to finally experience real world data. It is a large data set. You can do the Kaggle competition on the Kaggle web page or platform instead of using it on your own PC, as it may take some time to run due to the number of data sets or number of observation or how large the data set is. Right, so yes, we will be sharing that next week, and good luck for your current MCQ. And I will see you guys next week to give insights on the Kaggle competition. Cheers.